Our final lecture for nonlinear and non-normal models is on how to determine the distribution of your data. So no required readings, but a few optional ones. One that I want to point out is a paper that I wrote in 2016 where I use some of these methods for determining which distribution fit my data. And so if you want to look at any of that, you can check out the supplemental information or the paper at that link. So how do you know what distribution you should use? Sometimes you're in a situation where you have your data, but you don't know what distribution fits your dependent variables or your y's, and thus you don't know what approach to take for the rest of your analysis. So in a similar way before, where we were, for our nonlinear models where we were defining our y's as a function of our x's, we were basically using functional forms to fit our y's. Now we're trying to determine what distribution fits our y data. And to do this, you need a method for determining which distribution fits your data most appropriately. And so to do that, we're going to use maximum likelihood. To determine what distribution best fits your data, you need to use maximum likelihood estimation, which allows you to determine the maximum likelihood estimates, or your MLEs, of the parameters of the potential distribution that you are testing. These parameter estimates define the distributions so it most likely fits the data. And I want to note here that we try to maximize the log of the likelihood, but again note that in most cases people actually minimize the negative log likelihood instead of maximizing the positive log likelihood. And so we could go through a bunch of derivations of why you use the log likelihood and how you derive that for different distributions, but I'm not going to have you do that. I'm just going to tell you that this is the process that maximum likelihood uses. And if you're interested, there are some really great resources on the second slide of this lecture. So let's talk about the data we're going to be looking at. So this was from a restored prairie experiment where we tried to understand how the presence or absence of herbivores like voles or deer alter the movement of the native partridge pea, Camecrista fasciculata, away from source locations after we'd planted it. And so here is an image of partridge pea. And so to get you into the data a little bit more so you can understand it, we have experimental units that either allow or deny herbivores access to the restored prairie. So here we have a picture of a rabbit, and they were mostly kept out, but those green squares indicate units that did not allow herbivores in, and when there were no squares, then herbivores had free reign to eat any plants they wanted in those areas. And so what we did was we planted partridge pea in known locations, so we planted it in the centers of all of our experimental units. And over time, we watched as these individuals of this species moved out away from the source, and we measured the distance from the edge of that circle to each individual so we could get an idea of how far our species are moving. And so in this case, it's pretty difficult to try to understand just by looking at the data what distribution best fits our movement data or our y's, right? How far are the individuals moving? And when you look at this, I mean, it could be many different distributions. It's just really hard to say. And so what we do is we fit different distributions with an MLE. This is in the BBMLE package, and you can again check out all of the code under the hood, but we use the MLE2 function to fit different distributions. And so it's again an optimization process quite similar to our NLS that we talked about before. And so here we're fitting a normal distribution to our distance data, and so we're fitting it with a D norm where our parameters are mean and SD, and then we're defining those as mu and s, and then we, in this start equals list function, that's basically saying what values do you want to start your parameters at as it optimizes. And so here we're just taking the mean and the standard deviation of the actual data. And so here's a summary of the normal distribution. When we do the same for exponential, Again, we use here the D exponent, and our parameter is a rate parameter, which we then define where to start in our start list. We also tried Poisson, and here the Poisson function or distribution has a parameter lambda, which we define as L and then give it a value to start with. And then finally, we tried a negative binomial, which is quite similar to Poisson, but it also has not only a rate or central tendency parameter, but also a spread parameter. And so here we use DN binom, where we have two parameters, mu and size. And again, we define these in our start list, and that allows us to allow the MLE2 function to optimize. And sometimes, as with NLS, you can have trouble if your starting parameters are just really outside the scope of where your models are trying to optimize, where the models are trying to optimize your data. So you sometimes have to play around with that because they won't converge. But I suggest trying various things and seeing what works. And then again, you can get your summary of your different models, and you can tell if your parameter estimates are significantly different from 0, which honestly doesn't tell you a whole lot, but just knows that you're on the right track for trying these different models. And then we use AIC to determine the difference between all of our models. So again, we use the AIC tab function, put all of our fit models into it, and here you can see that the negative binomial is much, much better than all of the rest of them because it's 37 points different from the next best fit model, and that's outside that 10-point rule of thumb boundary that I mentioned before. So we can say for sure that of the models we fit, the negative binomial fits the best. And again, I will mention that AIC can only tell you what's best out of the models you've tried. So there could be another distribution that fits this data better, but we haven't tried it. And so if you're trying to figure out what would be good potential distributions to try, I recommend just looking at the functions, doing question mark MLE2, the function, seeing what distributions it allows, and then looking them up on Wikipedia and seeing if they might fit your data. And so as usual, we need to graph our data as well as the estimates of the distributions of our data based on the likelihood estimates of the parameters. And so here you can see that the actual data are plotted in a smooth fashion with the black curve. And then all of our 4 potential distributions are plotted on top of the data. And the orange is the negative binomial distribution based on parameters we optimized using the MLE2 function, and you can see it fits the data really well. So I feel pretty confident, given this graph and our AIC scores, that the negative binomial would be a good choice for using some generalized linear models in the future, moving forward with this non-normal distribution, the negative binomial. And this figure is a bit complicated and it requires pulling out coefficients from the models. And so I would recommend looking under the hood and seeing how I did all of this. It's plotted in base R, so you can see some of the old school plotting. I think it's just a little more clear than trying to fit it all into the ggplot set or style of graphing, so I wanted to leave it in base R because I think it's really nice and clear. So definitely check that out. And with that, there's no quiz for this lecture, and this is the last lecture for the week.